In this lesson, we're going to explore acyl substitutions, the reactions of carboxylic acids and acid derivatives. Carboxylic acid derivatives undergo acyl substitution, which is the replacement of an atom or a group attached to the carbonyl by a nucleophile. With the exception of nitriles, all carboxylic acid derivatives have an electronegative atom directly bonded to the carbonyl. As you can see in this general example, the electronegative atom can serve as a leaving group and can be replaced by a nucleophile in a substitution reaction. The mechanism of acyl substitution varies based on the type of nucleophile used. Acyl substitution with a negative nucleophile proceeds through a simple two-step mechanism. In the first step, the nucleophile attacks the electrophilic carbonyl carbon, breaking the carbon-oxygen pi bond to form an alkoxide. In the second step, the pi bond is reformed, forcing the expulsion of the leaving group to give the final product. Acyl substitution using a neutral, uncharged nucleophile is essentially the same, but inserts an additional acid-base step in the middle. The reaction again starts with the nucleophile attacking the electrophilic carbonyl carbon, breaking the carbon-oxygen pi bond to form an alkoxide. In the second step, a weak base removes a proton from the nucleophilic atom. The reaction finishes as expected, with the reformation of the carbon-oxygen pi bond and expulsion of the leaving group to give the final product. Understanding the relative reactivities of the different carbonyl types is critical for determining whether a given acyl substitution will actually work. When looking at the acid derivatives, the relative order of reactivity is largely dependent on the leaving group. In general, the better and more stable the leaving group, the more reactive the carbonyl. And remember, a weaker, more stable base will be a better leaving group. So here I show the leaving groups of the various carboxylic acid derivatives, arranged from best to worst. At the front, we see the large halogen atoms, which would serve as the leaving group from an acyl halide, followed by the carboxylate, which would serve as the leaving group from an acid anhydride, and then a large drop in stability for the alkoxide and hydroxide leaving groups associated with esters and carboxylic acids, respectively. At the end of the list would be the negative nitrogen leaving group associated with an amide. So here I show the actual reactivity order of all of the major carbonyl types. I've included aldehydes and ketones for thoroughness. Starting from the left, we can see that, as expected, the acyl halides would be the most reactive, followed by acid anhydrides, and then aldehydes and ketones, which undergo acyl addition, not acyl substitution. After that, we see esters, and then a bit of a surprise. Based on leaving group ability, we would expect carboxylic acids to be next, but instead, we have amides, and then carboxylic acids last. You'll see why carboxylic acids are actually the least reactive carbonyl type in an acyl substitution later on in this lesson. Like other nucleophilic substitutions, acyl substitutions are reversible. The reverse of an acyl substitution is also an acyl substitution. And just as with other nucleophilic substitutions, equilibrium will favor the displacement of the better, more stable leaving group. Another way to look at it is that a direct acyl substitution will favor products when the reaction leads to a less reactive carbonyl type. So here I have a few examples. In the first reaction, we see an acyl halide reacting with a carboxylate. And don't let the presence of two carbonyls fool you. The carboxylate is clearly the nucleophile. It simply is a nucleophile that also happens to have a carbonyl. In this reaction, the chloride of the acyl halide will serve as the leaving group, forming an acid anhydride. In this case, equilibrium will be to the right, favoring the formation of products. We know this because the acid anhydride on the right is a less reactive acid derivative than the acyl halide on the left, and equilibrium will favor the side with the less reactive carbonyl type. In the second reaction, we have the same acyl halide reacting with water. In this case, water would serve as a nucleophile, displacing the halide leaving group to form a carboxylic acid. Again, we would predict equilibrium to lean to the right, favoring products. The carboxylic acid on the right is a less reactive carbonyl type than the acyl halide on the left, and equilibrium will favor the side with the less reactive carbonyl type. In the third reaction, we have a carboxylic acid reacting with ammonia to give an amide and water. In this case, the reaction will essentially fail, equilibrium greatly lying to the left, favoring the reactants. We can predict this because the amide on the right is more reactive than the carboxylic acid on the left, and equilibrium will favor the side with the less reactive carbonyl type. As you can see from these examples, direct acyl substitution enables the transformation of one acid derivative into another acid derivative, as long as the product carbonyl is less reactive than the reactant. An unusual example of acyl substitution is the Claisen condensation. The Claisen condensation is the reaction of an enolized carbonyl with an ester. So in the example, you can see that we have two esters reacting under basic conditions to form a beta-keto ester through an acyl substitution. The reaction mechanism begins with the base-promoted enolization of one of the esters, and that means that the Claisen condensation requires at least one alpha proton on the ester. The enolate then serves as a nucleophile in a two-step acyl substitution with the ester. In the first step, the enolate attacks the electrophilic carbonyl carbon of the ester, breaking the carbon-oxygen pi bond to give an alkoxide. In the second step, the carbon-oxygen pi bond is reformed, expelling the leaving group to give the final product. The Claisen condensation is an important reaction because it's one of the few that results in the formation of a carbon-carbon bond. So now that we understand the basics of acyl substitution, we can explain why carboxylic acids are so unreactive. Carboxylic acids do not typically undergo any direct acyl substitution reactions, and there are two big reasons for this. First, as we know, hydroxide is a bad leaving group. The reaction of a carboxylic acid with a weak nucleophile fails because the reaction would result in the formation of an even more reactive carbonyl type. If we look at this example, we can see a carboxylic acid reacting with chloride to give an acyl halide and hydroxide. We know that chloride is a considerably better leaving group than hydroxide, and we also know that the carboxylic acid is a considerably less reactive carbonyl type than the acyl halide. So either way you look at it, the reaction will fail, greatly favoring the reactants over the products. The second reason that carboxylic acids are so unreactive in acyl substitutions is because of their relative high acidity. Let's take a look at what would happen if a carboxylic acid is treated with a strong nucleophile, one that should be reactive enough to displace the hydroxide leaving group. So here I show a carboxylic acid reacting with a very strong nucleophile, NH2-. The top pathway represents acyl substitution, in which the NH2- displaces the hydroxide to form an amide and hydroxide. Based purely on the leaving groups in both the forward and the reverse reaction, we would predict this reaction to be favorable. Hydroxide is a better leaving group than NH2-, and that's absolutely true. This reaction would favor products if not for the competing acid-base reaction shown on the lower pathway. In the lower pathway, we can see the NH2- acts as a base, removing the rather acidic proton from the carboxylic acid. The result is the formation of a carboxylate anion and ammonia. Our knowledge of acid-base chemistry would allow us to predict that this reaction would also favor products at equilibrium. In the reaction, the negative charge is transferred from a nitrogen to a more electronegative oxygen. When a carboxylic acid is treated with a strong nucleophile, there are actually two competing reactions possible: acyl substitution and an acid-base reaction. The acid-base reaction is considerably faster than the acyl substitution, making it kinetically favorable. But the acid-base reaction is also thermodynamically more favorable than the acyl substitution. If we look closely, we can see that both reactions result in the transfer of negative charge from nitrogen to oxygen, representing a stabilization of that negative charge. But in the lower acid-base reaction, we can see that that negative charge is further stabilized by resonance. That makes the products of the acid-base reaction more stable than the products of the acyl substitution, and that means that the acid-base reaction is also thermodynamically favored. Fortunately, carboxylic acids can be coerced to undergo acyl substitution through acid catalysis. In fact, most acyl substitutions can be catalyzed by the use of a strong acid. As you'll see, the acid-catalyzed acyl substitution enables otherwise disfavored reactions. So here I show a general example. You can see that the reaction is still just an acyl substitution. The green OR prime attached to the carbonyl is replaced by the purple OR double prime. If we look at the reaction mechanism, we can see that it follows the same protonate, do something, deprotonate sequence found in other acid-catalyzed reactions of carbonyls. The acid catalyst promotes the reaction in two ways, and the first occurs in the very first step. The reaction starts with the protonation of the carbonyl oxygen. The positive charge in the resulting intermediate greatly enhances the electrophilic character of the carbonyl. So after protonation, we do something. In the second step, the nucleophile attacks the electrophilic carbon of the carbonyl, breaking the carbon-oxygen pi bond. Next, we deprotonate. In the third step, a weak base removes the acidic hydrogen from the nucleophilic atom to give a neutral intermediate. And that completes the first sequence of protonate, do something, deprotonate. And that means we start over. First, we protonate. In the fourth step, the acid catalyst protonates the leaving group, transforming what would be a poor leaving group into a considerably better one. Next, we do something. In the fifth step, the protonated leaving group is displaced, assisted by a lone pair on an adjacent atom. All that remains is to deprotonate. In the sixth and final step, a weak base removes a proton from the carbonyl to give the final product. We'll conclude by taking a look at three of the most common and important acid-catalyzed acyl substitutions. First, we have the Fischer esterification, which is the reaction of a carboxylic acid with an alcohol under acidic conditions to form an ester. In this example, we can see acetic acid reacting with ethanol in the presence of an acid catalyst to give ethyl acetate and water as a byproduct. This reaction really exemplifies the importance of the acid-catalyzed acyl substitutions. Without the acid catalyst, this reaction would fail, and equilibrium would favor the reactants. We would predict this because the carboxylic acid on the left is less reactive than the ester on the right, and equilibrium will favor the less reactive carbonyl. The use of an acid catalyst enables what would otherwise be a disfavored reaction. In order to push the reaction towards the formation of products, a large excess of one of the reactants is typically used. So in this example, a large excess of ethanol could be reacted with acetic acid. The reaction would be pushed towards the products according to Le Chatelier's principle. Next, we have transesterification, which is the reaction of one ester with an alcohol under acidic conditions to form a different ester. In this example, we see ethyl acetate reacting with methanol with an acid catalyst to form methyl acetate and ethanol. Last, we have hydrolysis, which is the reaction of any carboxylic acid derivative with water, which usually forms a carboxylic acid. In this example, we have an ester reacting with water under acidic conditions to give a carboxylic acid and ethanol. Acyl substitutions are among the most biologically relevant of all organic reactions. So here I show how the human body metabolizes a fat. The process demonstrates several of the fundamental types of organic reaction and includes 3 acyl substitutions. In this example, we start with tristerin, a typical fat. If you look closely, you can see that a fat is actually a triester, having 3 ester functional groups. The first reaction in the metabolism of a fat is an acyl substitution, specifically the hydrolysis of the 3 esters. The reaction produces glycerol, a triol, and 3 carboxylic acids. These long-chain carboxylic acids are known as fatty acids. Each fatty acid is then broken down via a 5-step process. The first step is another acyl substitution. The carboxylic acid reacts with a thiol to form a thioester. The thioester then undergoes dehydrogenation, the reverse of a hydrogenation, to give an alpha-beta unsaturated carbonyl. The alkene then undergoes an addition reaction, specifically a hydration, giving a beta-hydroxycarbonyl. The alcohol is then oxidized to a ketone, giving a beta-keto-thioester. The last step is the third and final acyl substitution. The beta-keto-thioester undergoes a retro-Claisen condensation, the reverse of a Claisen condensation. This results in the formation of 2 thioesters, one of which is acetyl coenzyme A. The larger thioester is then cycled back into the process, which is repeated until the entire fatty acid is broken down into acetyl coenzyme A.